Imagine Earth without its global magnetic shield. Right now, our planet is wrapped in an invisible bubble, the magnetosphere. Born from motions deep inside Earth's liquid iron core. It deflects charged particles from the sun, sculpts the auroras, and reduces the rate at which high-energy particles rain onto the atmosphere and near-Earth space. If that field disappeared, the consequences would cascade through technology, biology, atmosphere, and the very way human societies are organized. First, let's separate timescales. A sudden, complete disappearance would shock satellites and power grids immediately. A slow collapse over centuries would give societies more time to adapt. Either way, the physical mechanisms unfold along similar lines. More solar and cosmic charged particles would reach low altitudes and near-Earth space. Magnetically trapped radiation belts would relax, and induced currents in long conductors, power lines, pipelines, undersea cables would change profoundly. Begin with space hardware. We rely on satellites for GPS, communications, weather monitoring, and finance. The magnetosphere reduces the flux of energetic electrons and protons that damage electronics and solar panels. Without that protection, satellite electronics would experience far higher rates of single-event upsets, latch-ups, and cumulative radiation damage. Many satellites are designed with modest radiation margins. They would either need thickened shielding or would suffer shortened lifetimes and abrupt failures. In the weeks and months after field loss, we would likely see cascading satellite knockouts, loss of GNSS timing and positioning, degraded communications, interruptions to weather forecasting and Earth observation, air traffic, maritime navigation, bank transaction networks, and emergency services that rely on space infrastructure would feel immediate disruption. The next immediate technological hazard is geomagnetically induced currents. Even today, large solar storms create ground-level currents that burn transformers and trip grids. Without a magnetic field, direct access of charged particle fluxes and enhanced coupling of solar events to Earth would increase the frequency and magnitude of induced currents. Transformers, long-distance transmission lines, and undersea cables would be vulnerable to overheating and failure more often. Grid operators would face a new baseline risk level, and the economics of maintaining a global interconnected grid would change. Some regions might harden infrastructure with distributed microgrids and shorter transmission paths, while others would experience repeated blackouts and lengthy recovery times. Now consider radiation at surface and near-surface altitudes. The magnetosphere today deflects many charged particles, but it is not perfect. Cosmic rays and solar energetic particles still reach Earth, and we are already exposed to a background flux. Without the global field, the flux of energetic particles at low altitudes would increase. Two immediate effects matter most. Radiation doses to high-altitude flyers and astronauts would rise, and the rate of atmospheric ionization would grow. Airline crews on polar routes, already operating with higher exposures, would face higher occupational doses. Commercial aviation might reroute flights equatorward, raising costs and travel times. Space travel would become far more hazardous. Low Earth orbit would host a harsher particle environment that complicates human missions and shortens spacecraft lifetimes. An important atmospheric consequence would be changes in upper atmosphere chemistry. Increased ionization in the mesosphere and thermosphere would favor the production of reactive nitrogen and odd oxygen species that can catalyze ozone destruction. The detailed response depends on solar activity and the chemistry of the upper atmosphere, but model studies indicate that ozone concentrations at some latitudes could decline, increasing the ultraviolet B flux reaching the surface. Increased UVB exposure carries direct biological impacts. Higher risks of skin cancer, cataracts, and damage to planktonic organisms that form the base of many food webs. The magnitude of those increases depends on how quickly the atmosphere responds chemically and whether other processes, like increased aerosols or changes in cloud cover, offset the UV increase. It's important to stress that ozone chemistry is complex. A missing magnetic field is not a guarantee of total ozone collapse in months, but it does raise the odds of regionally significant depletion and spikes in surface UV. Biological systems also rely on magnetism more directly than we often realize. Many migratory birds, sea turtles, and some fish use geomagnetic cues for navigation. If the ordered global field weakened or became chaotic, migratory species that depend on consistent magnetic maps would misorient or increase navigational errors. Short-term impacts could include disrupted migrations, breeding failures, and ecological cascade effects in systems tightly timed to seasonal arrivals. Over longer timescales, selective pressures would favor individuals using alternative cues, stars, smell, visual landmarks, or prompt shifts in migratory timing and routes. Human physiology is only indirectly affected by the field's loss, but infrastructure and economy create cascading health effects. Loss of reliable satellite-based communications and timing systems would impede emergency response, disrupt supply chains, and complicate medical logistics. Repeated grid failures and long power outages create healthcare crises. Refrigerated medicines and vaccines spoil. Hospitals operate on backup systems, and heating or cooling failures increase mortality in vulnerable populations. Material systems would also behave differently. Increased atmospheric ionization and particle precipitation into the auroral and mid-latitude regions would lead to more frequent electrical surges and localized conductivity changes. Corrosion and dielectric breakdown rates for exposed equipment could rise in some environments. Pipelines that depend on cathodic protection and long undersea cables would need redesign and more frequent inspection. What about climate? The magnetic field itself is not a climate control knob in the sense of greenhouse gases, but it moderates flows of energetic particles that influence upper atmosphere chemistry and potentially cloud nucleating processes. Some hypotheses suggest cosmic ray fluxes correlate with cloud condensation nuclei and thus cloudiness. Without the field, changes in ionization could alter cloud properties regionally and seasonally. The net climatic response would depend on complex interactions, altered ozone, surface UV changes, and cloud feedbacks, and is unlikely to be uniform. Expect regional reorganizations of atmospheric circulation and precipitation patterns rather than a simple global warming or cooling. Longer-term geophysical consequences are also relevant. Over geological time, a sustained lack of a global magnetic field increases atmospheric escape rates for charged species. Earth's atmosphere is massive and losing it is slow. But over millions of years, increased stripping, especially of lighter constituents, could thin certain layers or alter upper atmosphere composition. That's not an overnight hazard, but it changes planetary habitability on geological scales. Society-level responses and adaptations would be multifaceted. Near-term priorities would be hardening and redundancy for critical infrastructure, radiation-hardened satellites, shielded electronics, grounding and surge protection for grids, and distributed communications independent of GNSS. Aviation would reevaluate flight corridors, and space operations would demand greater shielding or revised orbits. Conservationists would monitor migratory species and consider assisted migration or other interventions. Urban planners might accelerate development of resilient microgrids and localized food systems to reduce dependencies on long supply chains. Technological mitigation ideas include artificial magnetic shields at strategic locations, a concept researchers have floated for protecting Mars or critical space assets. On Earth, localized active shielding is energetically costly, but targeted measures, magnetically shielded satellite enclosures, underground data centers, and selective electromagnetic barriers for vital substations are plausible near-term tactics. There are also social and geopolitical implications. Nations with robust industrial bases might rapidly retool, while less resourced regions could face disproportionate impacts. Global coordination on satellite replacement, Information sharing on space weather and rapid investment in grid resilience would be necessary to prevent cascading failures that cross borders. Finally, consider the role of contingency and contingency planning. Human systems are tightly coupled and often optimized for current risk envelopes. The magnetosphere's near-constant presence is a background condition we rarely think about until it changes. A disappearing field would be a stress test across sectors: technology, ecology, health, and geopolitics. It would expose vulnerabilities and push innovation, but also cause real suffering during the adjustment period. In sum, removing Earth's magnetic shield would not instantly render the planet uninhabitable, but it would transform the risk landscape. Expect accelerated satellite and grid failures, heightened radiation exposure at altitude, potential regional ozone and UV changes, disrupted animal migrations, and long-term atmospheric consequences. Adaptation is possible, but costly and uneven. The thought experiment reveals how a single planetary-scale invisible field quietly underpins much of modern life. If this episode made you curious about the hidden forces shaping our world, subscribe to the channel for more deep what-if explorations that trace one scientific twist to global consequences. Subscribe now to stay notified of the next deep dive.